I'm a fan of the 12 Days of Christmas, but I feel it's fallen out of favor because it's so recursive, repetitive, and boring. I like it though because I feel that it's writhing with potential. First of all, you can do math things to it. I like doing math things, so let's do some math things. On day number 2/3 plus all over 3, 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 you get the point. Mathematics gave to me a Galliformes finidae in a tree of family Rosaceae. And not the most catchy thing, but it's a start. The song is pretty linear. Each day has that day's worth of groups of items. It gets interesting, though, when you start trying to figure out more complicated things, like how many items you get on each day. On the nth day of Christmas, my true love gave to me, can you figure out how many items you get on the nth day? It's 1 plus 2 plus 3 plus ... plus n. You can draw it out like this, which is like half of this, so it's n squared plus n over 2 items, one of which is likely in a pear tree. Going through and singing all of it is kind of weird, so I probably won't because it's so boring and linear. No matter where you are in the song, as long as it's not at the partridge in a pear tree part, you know what's going next. 4 calling birds will always come right after 5 golden rings, which always comes straight after 6 whatevers. There are, of course, other patterns you could use, like an abacaba pattern. The one where every other thing is A, but if you ignore that, every other thing is B, and if you ignore that, every other thing is C. It describes all sorts of things and pops up where you would least expect it. If we're singing abacaba dabacabally and sing each item in 1 second, if we want all 12 items, that would be 4,096 seconds, yada yada. We'd be here for over an hour, so maybe not. We can also count how many ladies dancing or golden rings or partridges in pear trees you'll be holding on to by January 6th. So, for example, in all 12 days of Christmas, how many rings do I get? 5 golden rings, but there are 12 days and the first 4 don't have any rings, so that's 5 times 8, which means that I'm getting 40. 40 golden rings. For any quantity of item, it's the amount you get in 1 day times the amount of days you'll be getting it. So that's 13x minus x squared. 6 and 7 would have the most, each with 42. The birds and trees and old men with drums, though, only show up 12 times apiece. If we can solve how many items you get each day, and how many of each item you get after a certain amount of days, can we find one nice clean polynomial function to describe how many items you receive from day 1 to day n? I tried to tackle this problem, and my first thought was, yes, we should take the antiderivative of the function of how many items you have per day. Because here's a nice curve of how many items you have. So the area under the curve should be the function that we're looking for. And since you have 0 items on day 0, we know that there's no y-intercept. I tried it, and it doesn't work. If you really want to know, it's probably easiest to punch it into a cubic calculator. I spent about 3 hours trying to find a nice intuitive proof last week, and then the person who sits next to me in calculus just decided to graph it and find a cubic function of best fit. It's this mess. I tried to figure out how to prove it, but I didn't get very far. If you're a math enthusiast and want to try to prove what I couldn't, give it a shot. You might just stumble upon a Christmas miracle. On the 12th day of Christmas, my true love gave to me